My talk is about what we can learn from the brain in order to improve the AI to enable more safe and more automated driving. The human brain is a great and proven reference for automated driving. The roads, the signs, the whole setting for driving was designed for human brain and for human eyes. In Autobrains, we are developing a new kind of AI, the AI that takes us a few steps closer to the way human brains works. There might be a question, why do we need a new kind of AI? There is an amazing progress today in AI. We managed to generate, through AI, realistic videos. We can have a high-quality conversation with AI. However, when it comes to real-world AI problems, we still have challenges. The current progress in AI is taking us few steps away from the reference, from the brain. We are using more compute, we are using more data, and we are using more expensive sensors. So I suggest we take a closer look to the reference, to the human brain. Let's take a look at the difference between the artificial intelligence and the human intelligence. So first of all, we as humans use our eyes. The artificial intelligence system, the autonomous driving, are using very expensive sensors, cameras, lidars, and radars. The learning process is also very different. As humans, we learn as we go. We have a self-learning mechanism. AI systems are pre-trained. We use a lot of training, a lot of data, and a lot of labeling. The inference process, the real time, is also significantly different. The AI systems uses a very heavy neural network, and it uses all the resources all the time. Our brain has those context switches. We know how to switch based on different situations and scenarios, and to use different parts optimized for those different scenarios. And finally, while the AI system is optimized and trained for the average case, the human brain is very good in those long tail of edge cases. And we manage to deal with those different scenarios, with those complex settings and combinations. Now, if we try to take it to more technical terms and ask ourselves, what are the three key gaps that are the main differences between human intelligence and artificial intelligence, I believe we'll find that we are talking about these three. The first one is the edge cases. As we drive, we have a very complex environment, complex combinations, lighting conditions, occlusions. We need to make decisions in real time with very complicated scenarios and role players. So this produces a long tail of edge cases which are frequently appear. This is the first challenge of AI that is trained, again, as I mentioned, for the average case. The second challenge is the cost. Both the cost of the system that goes into the car, its computational resources, its power consumption, its form factor, but also the cost of developing the system and validating that. The training cycle and validation cycle, labeling the data, using large-scale infrastructure to train those heavy neural networks. And finally, we get to the third major gap, which is the interplay or the interface between the key two models that are responsible for autonomous driving, the perception and the decision-making. There is a lot of things going on in the industry, and still the industry looks for the right recipe to match and pair those two different models. So let me take you through the first challenge. When we talk about AI, we usually talk about one big neural network that is being fed with a lot of labeled data, and the training process is about optimizing the average error, about reducing the mistakes over the whole set. So on one side, on the side of the solution, we have this optimization for the average case. But on the problem side, the reality is that we have a long tail of the corner cases that quite frequently appear. They aggregate, and that's the mismatch. So we don't have a good solution for those edge cases because the neural networks are trained to minimize the average error over the set. The cycle for improvement and getting to this edge case is by feeding more data, by labeling more data, by adding more layers, more parameters, more operation to those neural networks, and using more compute. But again, we're talking about this long tail of edge cases, and when we think about investment in terms of resources, we are getting to this exponential problem. So in order to improve the system 10 times, we need to invest 10,000 of times in terms of labeling, data, and infrastructure. And that's why we see marginal improvements today in real-world AI problems when we are thinking about those edge cases. We see 5%, 10%, all those publications are talking about marginal improvements. The second problem is the match between those two models, the perception, the model that is responsible for mapping the whole environment to environmental model, understanding the road players, the road settings, and modeling that in 3D, and then feeding the next model in the pipeline, which is the decision-making model. Today, one approach is the ADAS approach, to keep those two models separately, while the first one produces the object list and attributes and feeding the decision-making model. This worked extremely well for level 2 kind of scenarios, but once we scale to more in the wild, to more open conditions, it's almost impossible to predefine what is needed from the perception in order to produce a good decision-making. So there has to be some sort of interplay, some sort of a closed feedback. And indeed, one of the trends in the industry, just recently, Tesla shifted to a completely different approach. Instead of having two different models, in their case, 3 models related to perception, and then a path planning and control related to the decision model and actuation, Tesla made a decision to throw away all the thousands of lines of code and have one giant end-to-end neural network. This neural network receives pixels, and it produces recommendation and actuation for steering, brake, and acceleration. So let's take a look at the 2 major trends on this topic. One trend is Elon Musk, who believes that the approach and the right recipe to autonomous driving is pixels in, acceleration, brake, and steering out. And the other one is the CEO of Mobileye, a leading perception player in the ADAS field, who believes that end-to-end approach is very dangerous for automotive world. It's not necessary, but it will also not solve the problem, as we are again dealing with a neural network, single neural network, with all those edge cases, growing amount of resources, and so on. From our side, from Autobrains, we agree with both of these 2 key players in their criticism one to another. So just a few view of how the human brains, what we can learn from the human brain in order to solve these challenges. The cost, the edge cases, and the match between perception and decision. The human brain is characterized by a few key capabilities. The first one is a self-learning. We are not learning to drive by sitting in a room and viewing billions of images labeled with bounding boxes around them. We learn as we go. We have this self-learning mechanism of clustering, finding common elements and common patterns in the data, and forming, without supervision, the right concepts to behave and to make decisions in the physical world. The second is the low compute and power consumption. While the brain is an amazing machine, it consumes around 10 watts, so extremely low power. It's also low compute. We have a lot of resources, but we have this adaptive nature of the brain. It finds the right elements for the right scenario, for the right context. And so while there are a lot of computational resources, only a small fraction of these resources is actually being used in real time for a given scenario. let's look deeper into the neuroscientific findings related to the brain. We know through the work of Jeff Hawkins, Marvin Minsky, and many other great people in the neuroscience world that even the human brain doesn't have a single model of the world. It is not one giant neural network. On the contrary, it's a large composition, it's a large ensemble of smaller brains, smaller neural networks, each responsible for this end-to-end processing. So that exactly brings us to the solution. We believe that the solution is a new kind of AI that has to solve these three issues. We call this AI liquid AI, and I will explain where the name comes from. So the first characteristics, which is fundamentally different from the classical supervised fixed deep neural networks, is the architecture. The today's approach are based on thinking or using a predefined architecture of a neural network with many, many layers that is being fed into this training process to find the right parameters. We are talking about emerging architecture during the learning process for those different branches and bifurcations to have the chance to address those edge cases on the architectural side. We're not talking about additional search of parameters or network parameter search. On the contrary, the idea is to split the large problem to smaller and smaller problems, and each of those problems are modeled by sub-elements within our neural architecture. So if you go back and we try to compare how the liquid AI is different in its ability to solve the edge cases, let's look again at this long tail graph, long tail of the edge cases. Instead of trying to push single large model into this area of diminishing returns, where we need to invest so much in order to improve a bit for the edge case, we are splitting the problems through this liquid architecture, and each element in the liquid architecture is responsible for a subset of those edge cases. So we can freeze some parts of the architecture and let the others optimize and solve. I would mention that the liquid architecture and the self-learning are extremely highly dependent capabilities. In order to enable self-learning, we need this approach of splitting a very complicated large problem into smaller problems. Since self-learning is all about learning for these subtle, sparse cues from the data, not from billions of labeled images. And on the other hand, in order to make the liquid architecture scalable to any problem, we need the self-learning. We cannot rely anymore on thousands of people labeling billion images as we want to get through these corner cases. So in Autobrains, the process is bottom-up rather than top-down. Instead of starting from labeling billion images, feeding it into neural network, we let the neural network find the commonalities within the data and create those clusters. You can see here clusters of pedestrians and riders and some false positive examples. And it creates those very complicated but very interesting structures. And when we come to the labeling phase, we don't need to label instances. We can just label clusters. Of course, this improves the whole process, makes it more automated and curated. Finally, if we think about beyond perception, about this end-to-end approach that Tesla is driving, we think about the modular liquid architecture approach. So you can see here two building blocks. One building block is this ensemble of narrow AI agents. Ensemble, very large number, about 400,000 small neural networks. That's a lot of resources. Each of these neural networks was trained to do the end-to-end. Again, pixels in, acceleration, brake, and steering out, similar to Tesla. But instead of doing it for every case, it does that for a certain scenario, like getting into roundabout, like keeping distance from the vehicle, like passing a junction or turning right. Now we have the perception router, which is responsible for picking the right brain for the right narrow problem. This perception router, during the learning phase, has built a vocabulary of all the different driving scenarios. And as I mentioned, it's a large but finite vocabulary of those scenarios. So it's a clustering process and mapping those scenarios to predefined signatures. So then during the inference phase, once it identifies a certain scenario, like in this case, getting into the roundabout, a certain brain, which we call a certain skill, is picked. And this skill is executing the whole process end to end. So solving the perception decision problem is basically based on one hand, limiting the problem for the narrow scenario, and then not breaking the problem to perception and decision, but keeping it within this contained end-to-end approach for the narrow use case. If we go for a second back to the biological reference for the biological brain, we can see that actually animals have very different perceptions from human beings and perceptions between them. So when they look at a certain image, they have different sensitivity to colors, to distances, to proportions, and different perception formed within their brains. In a similar way, our AI agents also form within those end-to-end narrow neural networks very different perceptions of the world. If you would take, as in this example, a skill, an agent that is responsible for keeping us in the center of the lane, it will care only about lanes. It will ignore everything else, but will become super sensitive to small changes and differences that are related for keeping the lane centering. So we believe this approach of modular liquid AI and skills is the right approach to gradually build on the progress that happened in deep learning and AI. And instead of solving the problem at one time, we can have this gradual evolutionary approach, building the perception router and starting for a small number of skills and then increasing them over time. So the idea is that the system is already fixed. We have this vocabulary of the world, and then we can train more and more skills in additive end-to-end manner. Of course, this makes the system also much more visible, explainable, and debuggable. We are not lost within this large black box neural network, but we can always pinpoint and trace the problem to a specific skill, and within a specific skill, to a specific signature. So to wrap up the problems and what we believe the liquid AI can solve, I presented 3 problems. The first one is related to edge cases, where the solution in our approach is a shift from general AI to this liquid AI that is managing to shift the flow of information to narrow AI agents. The second is the cost, and the cost is crucial. Instead of using all these agents all the time, we are using a very small number of agents at every given moment. So while we have a lot of computational resources like the brain, we pick the right brain for the right task. And the cost is marginal to the whole architecture. And finally, we have this winning fusion between having perception and decision within a single model, but on the other hand, breaking the problem to smaller and smaller problems. Thank you.
Igal, thanks a lot. Very interesting presentation. Maybe we have time for 1 or 2 questions here. First one with the most votes. Does the AI define the different neural networks, and does the router learn itself as well?
Yes. So first of all, the learning process actually starts from the routing, from learning the routing process. We start from a neural network that is not trying to solve the problem, but trying to map the world to those clusters, to those scenarios. It's a clustering problem. So step 1 is learning to cluster, to build this vocabulary. And then once we have this vocabulary, we use all the data that we have to route to the right agents that are still empty. They don't know how to behave. And they are learning in the end-to-end manner this specific scenario.
Mm-hmm. Next question. Probably the last one. Do you think vision only, Tesla's approach, is possible?
Yes, that's our belief as well. We believe that a vision only approach is possible, and it's also the best way to test the actual AI. We do believe that radars and lidars are extremely important, but they should be viewed more as redundancy. So the first step is to use AI to get with vision only to the human level driver. And then the radars and lidars can bring us further to the superhuman driver.